Hello friends, in today's video tutorial, I am going to discuss with you 8 multiple choice questions plus 1 problem solving on the topic impulse, momentum, and kinetic energy. The questions are considered high order thinking skills, so just watch, listen, and be clarified. Our first question: if the magnitude of your velocity is changing, what else is or are necessarily changing? We need one or more answers. For letter A, you have acceleration. Letter B, you have momentum. Letter C, kinetic energy. And D, impulse. Okay? So, if your answers are momentum and kinetic energy, then you are correct. Okay? But why is letter A not accepted? Or letter D, acceleration, impulse, are considered incorrect as far as the question is concerned? Here is our explanation. We know that acceleration is equal to delta V over delta T, where delta V is the change in velocity, all right? And that's usually expressed as final velocity minus initial velocity. So, does it necessarily mean that when the velocity is changing, all right, whether it's change in the magnitude of the velocity, change in direction, or change in both magnitude and direction, okay, nothing is specified here, but nevertheless, that's what we mean by delta V. Does it follow that if there is delta V, there must be a changing acceleration also? Well, we know that when a body is accelerating, it is because there is a net force acting on the body, and according to the law of acceleration, F net is equal to mass times acceleration. Okay, whatever is the net force, okay, uh, the resulting acceleration is directly proportional to F net. Okay, so when the F net is constant, it follows that the acceleration is constant. Okay, so going back to our argument, that if the velocity is changing, it doesn't necessarily follow that the acceleration is also changing. Okay, because there are two possible cases as a result of having a change in velocity. We could have a constant acceleration, okay, and that is uh, precisely because the net force is constant. But if the net force is not constant, then automatically the acceleration is also not constant. It can be changing. All right? We are used to assuming that the acceleration of a given body acted upon by net force is always constant. No? It's hard to analyze a problem that involves variable acceleration. All right. Now, for letter B, momentum. If the velocity is changing, we say that automatically the momentum is also changing. Although basically, we know that momentum P is equal to mass times velocity. All right. So if the velocity is constant, it follows that the momentum is also constant. But if the velocity is changing, then it should also follow that the momentum is changing. All right. A change in velocity automatically means that its momentum, the momentum of the body is changing. Okay, if the delta V is what do you call decreasing or negative, then it follows that the delta P is also negative. So for letter C, okay, kinetic energy. When the velocity or speed of a body changes, is there also a corresponding change in kinetic energy? Well, according to the formula for change in kinetic energy, delta K, which is equal to 1/2 mass times, okay, the difference in the square of the final speed minus the initial square of the initial speed. All right. So when the speed of a body is changing, all right, whether the body is speeding up or slowing down, then we will have a change in kinetic energy. That's quite simple, right? And lastly, impulse. Does it follow that when the velocity of the body is changing, it means that the impulse, okay, causing the body to have a change in velocity? Does it mean that impulse is also changing? Okay, this is how we analyze. Okay, why do you think the body undergoes a change in velocity in the first place? It is because, okay, an impulse, J, symbol for impulse, there is an impulse imparted on that body, which is the product of the net force and the time of interaction. All right? So, that causes the body to accelerate or to undergo what we call change in speed or velocity, and hence a change in momentum delta P. Okay? We cannot accept the possibility of having a changing velocity which causes the impulse to change. All right? So, impulse is the cause, all right? Changing velocity is the effect. That is the relationship we have between impulse and delta V, or change in velocity. It is the impulse, no, that's causing the change in velocity, okay, or a change in momentum. Now, well, there is a common notion that when impulse is determined, okay, numerically it is equal to uh, the value of the momentum. That's the common notion, that impulse is equal to momentum. Well, technically that is not correct. All right. Why? Um, when impulse is imparted on the body because of the net force, okay, the net force causes the body to accelerate or to undergo change in momentum. All right, not just momentum, but change in momentum. So this equation here is the more exact relationship between impulse and momentum. It is impulse being equal to the change in momentum, and not just impulse equals momentum. We have to correct this. This is a misconception. Okay, a misconception on the relationship between impulse and momentum. Some people call it the impulse momentum theorem. All right, but it has to be made clear. The impulse that's caused, I mean the momentum, the change in momentum, okay, is the effect of imparting impulse, okay, which causes the body to undergo a change in velocity. Okay, change in velocity divided by change in time, that's acceleration. Okay, we cannot have an impulse being imparted in our body and having no effect on the momentum. All right, so that cannot be accepted. Therefore, we mark it with an X. And what should be marked with a check is momentum equals change, or impulse is equal to change in momentum. I hope that is clear. Question number 2. If the mass of a sliding block is doubled and the speed is halved, what happens to the momentum and kinetic energy of this mass? All right. So we are given this table uh, for each option A, B, C, and D, describing what's going to happen to the momentum and the kinetic energy if the given condition is satisfied, uh, the, the mass being doubled and the speed is being halved. So is it letter A, momentum is doubled, kinetic energy becomes half? Or is it letter B, momentum remains unchanged and kinetic energy is half? Or is it letter C, momentum is half and kinetic energy is doubled? Or should it be letter D, momentum is doubled and kinetic energy unchanged? Alright, so what is the correct answer? It is option letter B. And why? Okay, this is how we're going to prove that letter B is the correct answer. Okay, using the formula for momentum, all right, um, P1 is equal to M1 times B1. In other words, when the initial momentum of a body is expressed as the product of the mass and the velocity v1, and we will assume that the initial momentum is one unit, okay, for simplicity. So what happens? If you're going to double, okay, if you're going to double the mass, and then the speed is half, it's like saying that the mass is twice the original. Okay, we will let the mass m1 be equal to 1 unit as well. So if you double it, we put here 2. For the speed, okay, originally the speed is, say for example, 1 unit. So it becomes now 1/2 of the original. Okay, and multiplying these two, mass and speed, to get the new momentum, you will notice that the new momentum is just equal to 1 unit. All right, 1 unit of the momentum P2. What's the original momentum? It's also 1 unit. So we say that the momentum has not changed at all. It is unchanged. Okay? Now, how about the kinetic energy? Okay, again, let's use the formula for kinetic energy. All right? Initially, for example, it's 1/2 times the mass and the square of the speed. Okay, again, for simplicity, let's say that the initial mass is 1 unit. Okay, the speed is 1 unit. So multiplying 1 times the square of 1 and then divide by 2, the answer is 0.5 unit of kinetic energy. Then what's going to happen to the kinetic energy, all right, if the mass is doubled and the speed is half? All right, so our illustration would be in this manner: 1/2 times twice the mass. Okay, we set the initial mass as 1 unit. Now we have here 2. All right, and for the speed, it's now half, but you got to square it. Okay, so what's this? 1/2 times 2, that's 1. What is the square of 1/2? It's 1/4 or 0.25. And if you compare, okay, if you compare the new kinetic energy K2, which is 0.25 unit, compare it with the initial kinetic energy, which is 0.5 unit, all right, we say that the kinetic energy is just half. Okay? Question number 3. A high-speed plane and an innocent bird had a head-on collision. Which of the following would be equal for the plane and the bird? We are looking for one or more answers. Okay? The key to this question is in fact Newton's law of interaction, okay, where we can imagine that the force exerted by the plane on the bird, okay, must just be equal to the force exerted by the bird on the plane. All right. So we are going to look at the choices or the options. All right. So here are the options for question number 5. Letter A, we have change in momentum. Letter B, we have impulse. Letter C, force of impact. And letter D, acceleration after impact. All right, so take note, we are looking for one or more answers. Okay, which among these choices are equal for the two bodies, the airplane and the bird? Okay, so um, just said that the key to this question is Newton's third law of motion. Okay, the correct answers therefore are, we have letter A, we have letter B, we have letter C. That's it. Okay, we don't consider letter D as the correct answer. Now, time to explain. Right. Newton's third law of motion, okay, is very clear. Okay, action is equal to reaction. The force exerted by the plane on the bird, that's FPB, is always equal but opposite to the force exerted by the bird on the plane. So, that explains why letter C, option letter C, is correct. Okay? The plane and the bird will be experiencing the same amount of force, okay, when they collide each other. Okay? Newton's third law is the answer or the key. Now, how about uh, letter B, impulse? Okay? This is the formula for impulse as we stated earlier. Impulse is equal to the product of the force times the change in time, also known as time of interaction. And so it's very clear, if the plane and the bird have the same amount of force, okay, exerted on them, then it follows that the impulse imparted to each of the two bodies, the impulse imparted to the bird, for example, is also equal to the impulse that's imparted to the plane. So this uh, having the same impulse is just a consequence of having equal but opposite force. All right? And how about letter A? So from the formula again on the relationship between impulse and change in momentum, all right? Where we say that impulse is just equal to change in momentum. All right. Therefore, it should also follow that if the impulse that each body, the airplane and the bird, would receive, okay, um, are equal, then it follows that their change in momentum or changes in momentum are also equal in magnitude, but not acceleration. Why? Why is acceleration not considered? Look at this relationship of acceleration. Let's say AP is the acceleration of the plane, all right, just after their collision. Now, since F is the same or constant, but we have a bigger mass for the plane, All right. Okay. So the the hugeness of the mass of the plane is emphasized in this equation. All right. When the force F is divided by a big quantity mass, what do you expect to happen to the acceleration? Okay, A is inversely proportional to the mass. We know that. With constant F, as you increase the mass, the acceleration will be very small. And that's not surprising. Okay, we know that the plane, when it hits the bird, the plane is hardly affected at all. Okay, it would have an acceleration. Why not? Okay, but it is not noticeable. Okay, who gets the greater acceleration? Of course, the other body. Let's assume that the mass of the bird is too small. Okay, so again, it's being emphasized here. The mass of the bird is too small as compared to the mass of the plane. But with their equal amount of force exerted, this what's going to happen? If a constant amount of force is divided by a very small amount of mass, what's going to happen? Small mass will result to, okay, a larger amount of acceleration, which is true because during collision, it is the bird that's going to undergo a high change in velocity. We call it acceleration. So the two accelerations therefore are not equal. Okay, that's why option letter D was not considered correct. In question number 4, a heavy truck and skateboard are moving at the same constant velocity. Which of the following statements is true about the truck and the skateboard? All right. So the key word in this question is that uh, both the truck and the skateboard are moving at the same constant velocity. So take note, the same constant velocity. And we're looking for the statement that is considered correct or true. Okay. Is it letter A? They both have acquired zero impulse. Letter B, they have equal momentum. Letter C, compared to the truck, a skateboard has a greater momentum. And option D, compared to the skateboard, the truck requires less stopping force. Okay, what do you think is the correct answer? It is letter A. Okay, let's explain why. Constant velocity, as specified in the question, means that the acceleration of the body is zero. Okay, and the F net acting on it is also equal to zero. Okay, so because of this, if there is no acceleration and there is no net force, the two bodies, okay, are just moving with constant velocity. Okay, let's first explain B, C, and D. Okay, so given this situation, do we say that the two bodies have equal momentum? Okay, let's recall again the meaning of momentum. The product of the mass times the velocity. Okay, so this equation applies to the heavy truck. So the heavy truck, because it has a relatively bigger mass, all right, with uh, a velocity that is, uh, well, the same as that of the skateboard, okay? But because of its bigger mass, we expect that its momentum would be large, okay? That is the meaning of this equation. And how about the skateboard? Because it has a relatively small mass, and they both have the same velocity as the truck, then naturally, okay, when you multiply a small mass by a constant velocity, then you will expect that the momentum of the skateboard will just be small as compared to that of the truck. All right? That makes letter B an incorrect option. Okay. How about letter C? Okay. We can also base our reasoning on these two equations. Compared to the truck, the skateboard has a greater momentum. All right? Is it true that the skateboard has the greater momentum? Look at the way the symbol of the momentum for each. Okay? Their symbols are written in such a way that we are emphasizing, okay, momentum of the truck is much larger than that of the skateboard. That's why letter C is incorrect. All right. Now, speaking about option D, it talks about stopping force, okay, which between the skateboard and the truck requires the less stopping force. Again, we will recall, um, or that is our conclusion, okay. In comparing the momenta of the two bodies, we say that the momentum of the truck is larger than the momentum of the skateboard. Now, okay, to describe the force or compare the force, stopping force, okay, uh, required to stop, okay, to stop the two bodies. Again, we are emphasizing the difference in the what do you call this, the mass, okay. So according to this formula, change in momentum is equal to the product of the mass times the change in velocity, which is also equal to the impulse. The product of force times time is known as impulse. And very clear in this equation, okay, that the amount of force F, okay, this represents the stopping force in order to, for example, uh, change the momentum of the body, okay, there is a need to apply a force, okay. So a large force is required to stop, okay, a body with bigger mass, okay, with constant change in velocity and constant time of interaction, okay, a bigger force is required for a bigger mass to stop, or for that bigger mass to undergo a change in momentum. Okay? The bigger mass will also have the greater change in momentum, which corresponds to a bigger stopping force. That is why what is described in option D is quite the reverse. Alright? Compared to the skateboard, it says the truck requires less stopping force. It should be the other way around. Okay? Or you can say that the truck requires greater stopping force. Before we proceed to question number 5, I almost forgot to explain to you why letter A was considered our correct answer. All right. So if you bring back the formulas that we already or that I have already shown to you earlier, okay, what we need in explaining option A is the fact that the bodies, the two bodies are moving with constant velocity, where we emphasize that when a body is moving with constant velocity, its acceleration is zero, and that there is no F net or external net force that is acting on the body. Okay? So it follows that when there is no net force acting on the body, okay, there is no impulse, right? There is no impulse imparted to either the truck or the skateboard. You understand? No net force has been exerted because during during the what do you call this? During the time that we are describing these two bodies in motion, okay, uh, their their respective velocities was kept constant and in fact were equal in magnitude as well as in direction. So that simply means that both the heavy truck and the skateboard have not undergone any change in uh, velocity and therefore no F net whatsoever, no net force, and so no impulse, okay, was imparted on each one of them. That makes our answer in letter A the best answer, okay, for this particular question. That is, they both have acquired zero impulse. For question number 5, a 1 kilogram ball is dropped from a certain height. It hits the floor with a downward velocity of 2 meters per second and bounces with an upward velocity of 2 meters per second. What is the ball's change in momentum? Is it letter A, 4 kilogram meter per second upward? Or is it letter B, 4 kilogram meter per second downward? Or should it be letter C, 2 kilogram meter per second upward? Or option D, 0? Okay, so our answer is letter A. And this is how we got that particular answer. We're looking for the ball's change in momentum. Okay, and the formula for delta P, or change momentum, is simply the product of the mass times uh, the, the, the change in the velocity, or V final, minus V initial. Okay, so we plug in the quantities into that formula. Okay, 1 kilogram for the mass, and then positive 2 meters per second for the final velocity. Okay, positive because we're talking about the upward direction of the velocity mentioned in the question. Minus, okay, minus quantity, negative 2 meters per second, because the initial direction of the velocity, according to the problem, is downward. All right. And we have an agreement that downward velocity should be represented by a minus sign. So what's going to be the result when we are going to do our algebra? Okay. Delta P, therefore, the change in momentum would be positive 4 kilogram meter per second. So that's the solution to this particular question. And letter A is the correct answer. Okay, our next question is, a stuntman jumps from the roof of a tall building, but no injury occurs because the man lands on a large field or airfield bag. A large airfield bag. Now, which of the following best describes why no injury occurs? Okay, the bag, letter A, provides the necessary force to stop the stuntman. Letter B, the bag reduces the impulse imparted to the stuntman. Letter C, the bag increases the time of impact and reduces the force on the stuntman. And letter D, the bag increases the time of impact and reduces the pulse or the impulse on the man. All right. So, what is the best answer here? It is letter C. Why is the letter C considered the best answer? The bug increases the time of impact and reduces the force on the stuntman. Okay, here is the explanation. We base it from the formula of what we call impact force. This formula for impact force is a derived formula taken from the definition of impulse equals change in momentum. Okay, you will notice here that the variable delta t or time t has been moved to the right side of the equation for the impulse change momentum equation. So it's now in the denominator. Okay, since we are interested in describing the amount of impact force, so we put the time of interaction on the other side of the equation. Okay, so now we have F equals the mass times the change in the velocity v final minus v initial all over the time t. And based on this formula, it is pretty obvious that the force of impact is inversely proportional to the time t. And that's exactly the meaning of option letter C. That is, we have an increase in the time of impact. Okay, the time of impact between your body or between the stuntman's body uh, with a large airfield bag. Okay, the large airfield bag is probably kind of soft. Okay, not hard, so that during the fall or when the stuntman jumps and hits the large airfield bag, okay, uh, it takes relatively longer for them to interact. Okay, the time of impact is being lengthened or being increased, and as a result, the consequence of that is to make the impact force smaller. Okay, smaller. In the formula, the mass and the change in velocity are supposed to be kept constant. Okay, and that really is what is happening. Okay, because the stuntman uh, who has a particular or specific amount of mass and the change in velocity. Okay, you can imagine that the change in velocity would not change at all. So keeping them constant but increasing the time of interaction will make the force smaller. All right. All the other explanations A, B, and D are definitely not considered correct explanations. All right. So this is the best explanations why we don't get hurt. For example, when we uh, um, when we jumped, okay, when you try to jump and land on concrete pavement, what do we normally do? Okay, uh, we sort of what do you call that? We lessen, no? We lessen the force that the floor will exert on us. How? We usually bend our knees. So by bending our knees, we are increasing the time of contact between our legs and the floor or the surface, the ground, making the impact force not so uh, not so large, no? Some amount of force that we can tolerate and that we don't get hurt. So that's exactly the same situation as what we are trying to explain here. All right, impact force is what gives you the pain. Okay, the larger the force of impact, the greater the pain during collision. Question number 7. We have an object of mass 3m. Initially at rest, then it explodes and break into two fragments of mass 2m and 1m, respectively. Question is, which of the following statements concerning the fragments just after the explosion is considered true? All right? So which among the four statements here is correct? Letter A, they fly off at right angles, meaning the two fragments just after the explosion. Okay, letter A, they fly off at right angles, meaning 90 degrees. Letter B, they fly off in the same direction. All right. And letter C, the mass m, all right, or 1m, will have twice the speed of 2m. Okay? And letter D, 2m will have 2 times the speed of m. So C and D are quite the reverse of each other. All right. So how do we analyze and answer this question? But first, let us reveal the correct answer. The correct answer is letter C. Okay, the smaller mass, the single mass m, will have twice the speed of 2m. Why is that so? Here is our um, solution. All right, we will let the original mass before the explosion happened. Let the original mass be equal to 3 kilograms. Okay, an object of mass 3m, it says there, mass of 3m. So we will let that be the original mass, 3 kilograms. And then also stated there that the initial velocity of the original mass is 0. All right. So what happened after they explode and broke into two fragments? After explosion, okay, we now have two fragments. From a single body mass of 3 kilogram, we now have two, okay, separate fragments. One has a 1 kilogram mass, the other is twice, okay, which is 2 kilogram. M1 is 1 kilogram, M2 is 2 kilograms. And then we will also assume, okay, for simplicity, we will assume that the smaller mass will acquire a velocity equal to positive 1 meter per second. Okay, v1 prime here denotes the velocity after the explosion, right? Then we're going to look for uh, the velocity of the other mass, the bigger one, okay, after the collision. That will be our unknown variable, okay? So we'll now proceed with our computation. And the concept that we're going to apply here is what we call uh, the law of conservation of linear momentum. For this particular situation, we are talking about explosion, all right? So the equation is simply uh, total momentum of the two bodies before they explode must be equal to the total momentum of the two bodies after the explosion. Okay? And since initially the original mass, 3m, was at rest, all right? It follows that uh, the total momentum before the collision is equal to zero. Okay? Since there was no velocity. Okay? No velocity, no momentum, zero. Now, uh, the total momentum after the explosion is what we're going to uh, use here, okay? Which is equal to the sum of the two momenta, momentum of the smaller body or smaller mass, plus the momentum of the bigger mass after just after they exploded, okay? So that means 1 kilogram, the mass of the smaller mass, multiplied by um, what's this? It's it's uh, it's velocity after the collision, okay, 1 meter per second. Then plus the mass of the bigger mass, all right, or the bigger fragment times the unknown variable, uh, the velocity after explosion, and then we equate it to zero, all right, because we already stress here that the total momentum after is just equal to the total momentum before, which is equal to zero, okay? And when we have this kind of equation, okay, the two terms here are added and then equated to zero, okay, we just isolate one of them, put them on the other side of the equation, just like what we have here. 1 kilogram meter per second is equal to the negative, okay, of 2 kilogram times b sub 2 prime, or the final velocity of the bigger mass. Now it has a negative sign because what we did was to uh, put this on the other side of the equation, all right? So this is now what's going to happen. Since we're looking for v2 prime, the final velocity of the bigger mass, what we normally do is divide both sides by negative 2 kilogram. We do that, uh, the negative 2 kilogram on this side will just be cancelled, okay? And that will just give you the unknown variable v2 prime here. But on this side, when we divide 1 kilogram meter per second by negative 2 kilogram, then the answer would be kilogram, the unit kilogram cancels out, okay, and 1/2 is just equal to 0.5, okay. We bring down the negative because that's 1 over negative 2, okay. Negative 0.5 meter per second is our final v2 prime, or the velocity of the bigger fragment just after the explosion. Okay, so this uh, reaffirms our answer in the previous slide, we said that the answer was that uh, the velocity after explosion of the bigger mass will just be half. Okay, will just be half of what the smaller mass would actually have after they exploded. Since we assume that the smaller mass would be having a positive um, velocity after the collision of 1 meter per second, then logically the other body would have an opposite velocity, okay, which has a magnitude that is just half the value of uh, the, the value of that of the smaller mass. So this this proves our answer earlier. Okay. For question number 8, which types of collision given in the table best satisfies the validity of the law of conservation of momentum and the kinetic energy conservation law? So, for letter A, kinetic energy conservation law is valid if the elastic collision uh, only if the collision is elastic. That's what is meant by option A. Only if the collision is elastic. Okay. In other words, it doesn't apply to inelastic. But the momentum conservation, okay, will apply only for elastic collision. Okay. Now, for letter B, okay, kinetic energy conservation applies only for inelastic collision. And the momentum conservation law, okay, applies for either elastic or inelastic collision. Now, for letter C, kinetic energy conservation only applies to an elastic collision. Okay, and for the momentum conservation, again, it's either elastic or inelastic. Okay, the option D, kinetic energy conservation applies or valid, valid for either elastic or inelastic. And similarly, the momentum conservation also is valid for either elastic or inelastic collision. Okay, so with a little analysis of what you know about these two conservation laws, I'm sure your answer would be letter C. All right, that is the correct answer. As we all know, kinetic energy conservation, okay, is only valid. We only apply it, okay, when the collision or explosion, okay, involves elastic collision. It doesn't apply to uh, inelastic collision. In other words, if the collision is inelastic, the kinetic energy of the system, okay, is not conserved. Okay, uh, it may it may be that the what do you call this, the kinetic energy, okay, is less than in the or after the collision, the kinetic energy of the system is less than that of the total kinetic energy before the collision. Okay, that is what is meant by our answer here. You will notice that uh, for conservation of momentum, it doesn't matter. Okay, I'm sure you know this. The law of conservation of momentum, okay, applies to whether the collision is elastic or inelastic. So it's only the kinetic energy conservation, okay, which has a limitation, okay, only valid if the collision is elastic. This is now the last question, okay, but this time it's no longer a multiple choice question, okay, it's more of computational. So we are given a figure that shows an elastic collision of two particles A with a given mass m1 equal to 0.500 kilogram and particle B with a mass m2 equal to 0.300 kilogram, okay, on a frictionless surface. Okay, so particle A has an initial velocity of 4.00 meter per second in the positive x direction and a final velocity of 2.00 meter per second in an unknown direction, which we label here as alpha. Okay, that's actually the angle known as or denoted by the Greek letter alpha. Particle B is initially at rest. Okay, so you have to find the final speed of particle B and the angles alpha as well as beta. So in our diagram, as you can see here, before the collision, this is the situation. All right. So particle A is moving to the right with that velocity of 4 meters per second, while particle B is at rest. So it has no velocity. There's their masses. Now, after the collision, okay, after the collision, what happens is that particle A is now moving, okay, with a velocity final equal to 2 meters per second. Okay. Before collision, it was actually moving uh, at a greater speed of 4 meters per second. But now, when it collided with particle B, it's now uh, moving with a lower, okay, speed, 2 meters per second, and the direction of the motion after the collision is denoted by the angle alpha with the horizontal. All right, so that is what one of the unknown variables that we're going to calculate. Now for particle B, it also, uh, what do you call this? It also deviated, no, from moving along a straight path. Okay, its magnitude of the velocity after collision, okay, um, is not given. So that is what we are going to determine as well. And of course, its direction denoted by a Greek letter beta. Okay? So let's take a look at our initial solution now. Okay? So since the collision is considered elastic, we apply the conservation of kinetic energy, which says that uh, before the collision, okay, the sum of the two kinetic energies of the particles, K1 and K2, must be equal to the sum of their kinetic energies after collision. Okay, uh, K1, K2 with a prime, okay, indicates that these are the kinetic energy after the collision, right? And expressing the kinetic energies in terms of 1 half mv squared. So we have there 1 half the mass of the particle A, but we use here the subscript 1 instead, all right? And then the speed initial, meaning the speed or velocity, but it's more appropriate to call this speed because kinetic energy is a scalar quantity. So it must be associated to a scalar quantity as well, which is speed. Square that, okay? And then uh, the initial kinetic energy of particle B is no longer included in the equation because anyway it is equal to 0. Alright? So equate this to uh, the kinetic energy of the first particle, particle A, after the collision, 1 half m1 b1 squared and then with a prime. Alright. Plus the final kinetic energy, okay, this is the kinetic energy of the second particle, particle B, after being hit, okay, or after the collision. So this is also with a prime. So that's our working formula. And you might notice that all terms in the equation have one half, one half, one half. All right. So we can cancel the one half here and simply have this working equation in finding the final velocity v2 uh, prime, meaning the velocity of particle B after the collision, but still this has a square or an exponent there, okay, and that is now equal to m1 b1 squared minus m1 b1 squared prime. All right. In other words, we isolated from the original equation the term b2 squared prime because this is one of our unknown variables. Okay, so we'll be dividing by the mass of the particle B. Now, when we proceed, okay, it's kind of long substitution of the given, no, in the formulas. So there you have the mass of the first particle, okay, in kilogram. Okay, multiply it by the speed, okay, the speed of the small particle, the speed of the small particle squared, 4 meters per second. Then minus, uh, this term here refers to the kinetic energy of particle A after the collision. So that's the mass there. We have 0.5 kilogram and then multiplied by the velocity of particle B after the collision, but you have to get the square of that. All of this inside the bracket, okay, will be divided by the mass of the bigger mass. I mean the particle B, whose mass is 0.300 kilogram. Then simplifying, all right, doing your algebra, okay, we will get the value for V2 prime, which is in three significant figures, 4.47 meters per second. All right. So as indicated earlier in the drawing, all right, that B2 prime, uh, whose value is 4.47 meter per second, the direction of that, okay, is described by angle beta. Okay, angle beta. As soon as we are able to determine the angle, then we will be able to fully describe the complete what do you call this, the complete direction, okay, of the final speed of particle B. So in the meantime, we will proceed, okay. So um, to determine the angles alpha and beta, okay, the second concept, or the law of conservation of momentum, is what we're going to apply, okay. But since you must have noticed that this kind of problem is a two-dimensional problem in law of conservation of momentum, okay. In other words, there are components of the momentum for both particle A and particle B. We have the x component and the y component of their final velocities. So what we will do first is, uh, what do you call it? Determine the equation, okay, based on the momentum conservation. Okay, we will describe the uh, total momentum of the two bodies, particle A, particle B, okay, along the x-axis, that is, x component. And this is how it's written, okay. It's just the usual formula for conservation momentum, but we notice that there is a subscript x, okay, used for the velocity. So to emphasize that we are talking about the x component, all right. So when we substitute there, we are emphasizing that this is the x component part of the momentum conservation, okay. And if you're going to substitute following that formula there, where we have the mass of the smaller particle, zero point 0.5 kilogram, multiplied by its initial speed, 4 meter per second, or I should say velocity, all right? And then equate that to the mass of uh, the smaller particle, but multiplied, okay, multiplied by its final velocity after the collision, okay? So 2 meters per second was given, okay? But since we're talking about the x component of the velocity, okay, we want the x component here, v1x prime, okay? So if you refer back to your to the figure, the x component, okay, of the velocity is just equal to the product of 2 meters per second and the cosine of the angle alpha. All right, cosine alpha, which is, I mean, alpha is yet to be determined. Okay, so that's equivalent to that part there. And for the second, the momentum along the x, okay, the component or the x component of the momentum of the bigger particle, particle B, after the collision is also now expressed in their respective quantities, like the mass of 0.3, all right. Uh, I think I stand corrected. This refers to the mass of the smaller particle, all right, because it says there 0.3 kilogram. The first one was zero point 0.5 kilogram, so this is the smaller particle. And that is multiplied by 4.47 meter per second times the cosine of the angle beta. So in other words, this portion here is uh, the equivalent of the x component of the velocity, okay, for the smaller particle. Still, it's still cosine, but the angle now is angle beta. Okay, so how do we proceed? If you're going to simplify this equation, since there are two unknowns, all right? There are two unknowns in this equation. We don't know what angle alpha is, and we don't know what angle beta is. So let's first simplify, and then we will see how we're going to proceed. Right now, it looks quite difficult to figure out, okay, what we'll be doing next because of the presence of the units here. So I think for simplicity, or to make it easier, let's remove the units for the meantime. All right. So if you do that and then start multiplying, like for example, zero point 0.5 kilogram multiplied by 4 meter per second, not what do you call this? Discarding the unit first, then we will just get 2, all right, as the product of this zero point 0.5 and 4. We get 2, okay? And then equals, again, the product of zero point 0.5 and 2, which is 1. We discard, or we discard the unit first, and then we have there the cosine alpha. So 1 times cosine alpha, and what comes next? This one, all right? Because we are still have to add this part of the equation. Zero point 0.3 multiplied by 4.47, okay, disregarding the units, all right, will give us 1.34, okay, and that's to be multiplied to cosine beta. You see, the equation now is simplified, and it looks easier, okay, to figure out without the units in them. All right. Uh, in my experience of teaching this topic while doing problems, I usually advise my students, no, to do away with the units as long as they know that the variable that they are looking for has this particular unit. So during the process of the computations, since we are just doing our math, okay, the mathematics part here, you don't have to make it so complete with all the units included, no? To make it easier. All right, so how do we proceed? Let's see. What do we have here? Um, since we will first determine one of the angles, so I just transpose. I just transpose this term 1.34 times cosine beta on the left side, or to the left side of the equation, and then the uh, the 2 here, this is actually 2 kilogram meter per second, okay, is placed on the right side. If we combine this part, 1 times cosine alpha with 2, okay, they become like this, 2 minus 1 cosine alpha. Okay, so I hope you are able to follow. And simplifying further, so what does this mean? Okay, what I just did here actually was to square the whole all of the terms in this equation, okay, are being squared. And if we do that, all right, we get the square of 1.34 is 1.80. Of course, the square of cosine beta is just cosine squared beta, all right? And in squaring these uh, terms on the right side, it's just like multiplying this 2 minus 1 cosine alpha by itself. All right. Okay. So if you do that, this is what we're gonna get. We get, because the square of 2 is 4. All right. And then how did we get negative 4 cosine alpha? Because when we multiply 2 by 1, okay, cosine alpha, we get negative 2 cosine alpha. But we'll be multiplying that twice. Okay. I'm sure you know what I mean here. All right. When you do your algebra, when you multiply this by itself, no, the whole thing, you're gonna get this minus 4 cosine alpha. And then there's that plus cosine squared, because part of the process is for you also to get the square of cosine alpha, and that's cosine squared alpha. All right. So uh, from here, we just isolate. Okay. We just isolate. Again, we isolate the terms such as cosine squared beta. We put you isolate it in such a way that it only appears all by itself on the left side. So what did we actually do here? We just divide all terms by 1.80 or 1.80. Okay, so in here that cancels. Okay, we just get cosine squared beta. But all of this will be divided by 1.80, and the result is 4 divided by 1.80 gives you 2.22. Similarly, that's minus 4, so 2.22, and then put down the cosine alpha, all right? Then plus. This is understood to be 1, right? 1 cosine squared alpha. So that has to be divided also by 1.80. And what we get is 0.556 cosine squared alpha. Okay? We are not done yet. This will be continued in the next slide. All right, continuing with our computations, uh, we were able to simplify uh, the equation that we needed, no? Okay, in order to find the angle, specifically the angle beta. So we still have another um, unknown variable, and that is the angle alpha. So there are two unknowns, the two angles, alpha, beta, so we still need another equation, and that comes from determining the equation for the y component, all right? The y component can be written like this, okay? This pertains to the conservation of momentum considering the y component, okay? So what we have here is that the momentum before they collided, right? Before the two particles collided, their total momentum along the y, right? That is along the y was 0. Okay, and then this is equated to the total momentum after they collided, considering the y component only. So again, just like earlier in the case of the x component, we also label here the velocity with a y symbol. Subscript is y. All right, to emphasize, we are now we are now considering the equations for the y component. So with that, we again plug in all the given quantities for the mass, the larger mass, that is 0.5 kilogram multiplied by the final, okay, this is the final velocity of the bigger mass, okay, supposed to be along the y, but since the 2 meter per second given in the question, okay, actually makes an angle, okay, makes an angle alpha, and what we want is the y component. So we multiply that to the sine of the angle alpha, okay, and then for the other, what do you call that? For the other quantity of the y component, okay, we have also this one. Uh, this becomes minus because now the y component for the momentum of the smaller mass is now uh, downwards or to the negative y axis. And hence, we have there the minus sign. So the mass was zero point 0.3 kilogram multiplied by the, uh, what do you call that? The velocity, 4.47 meter per second, which makes an angle beta. But what we want is the y component, so we are using sine of the angle beta. When you multiply it to 4.47 meter per second, that's exactly uh, the y component of the velocity, okay? Which when multiplied to the mass, of course, will become the y component of the momentum in the y component. And to proceed, we just isolate, all right? Put the this term here on the left side, okay? And when we multiply zero point 0.5 by 2, okay, that's written down here on the right side. Zero point 0.5 times 2 is 1 kilogram meter per second, okay? And of course, you put down the sine alpha, okay? This one here was written on the left side. 0.3 times 4.47 actually gives you 1.34. Okay, and sine beta is also put down here. And just like what we did earlier, we, for the meantime, get away with the units to make it look simpler. All right, there. And what what we did do earlier for the x component? How did we proceed? Okay, we also squared, okay, this equation. So when you square this equation, the square of 1.34 is 1.80. Sine beta squared is sine squared beta. And this one looks simple or simpler than what we had earlier because we simply have 1 sine alpha, square this, and we get 1 sine squared alpha. All right? So that equation is further simplified by dividing the whole thing by 1.80. Okay, that makes us uh, or that will allow us to isolate sine squared beta and put it on the left side by dividing 1.8. I mean dividing the whole thing by 1.8. And if we divide 1 divided by 1.8, that's actually what how we got 0.556. And we simply bring down sine squared alpha. Okay, so this is the what do you call this? The equation. Okay, this is the equation where we make use of the y component, and we label it as equation 2. Okay, earlier we have equation 1. This is now equation 2. We need two equations in order to determine the two variables, angle alpha as well as angle beta. Okay, now let me see. This expression that I have here is the equation 1 presented to you earlier, and we are going to combine them, all right? Combining the two equations, or adding the two equations, but considering an important trigonometric identities, okay? There is a trigonometric identity which says the sum of sine squared alpha, okay, or beta, I should say, sine squared beta, when added to cosine squared beta, their sum equals 1. And that's what I'm going to apply here. When we add these two equations, okay, add equation 2 to equation 1, meaning when we add sine squared beta plus cosine squared beta, what do we get? All right, we are going to get a value that is equal to 1. And then similarly, we will also add the other, what do you call that? These other terms in the equation, 0.556 sine squared theta, all right? Uh, there's another 0.556, but this is cosine theta, or cosine squared theta here, okay? So when you combine these two equations, what will we get? All right, so how do we determine the two angles, angle beta and angle alpha? All right, so we use the two equations that were earlier presented. Here they are. All right, equation 1 and equation 2. Okay, what's going to happen if sine squared beta is added to cosine squared beta? Okay, so as I was explaining earlier, uh, a trigonometry identity tells us that their sum must be equal to 1, right? So combining the two will result to a more simplified equation, which allows us also to eliminate the angle beta, or the variable beta. Okay, sine squared beta plus cosine squared beta is equal to 1. And similarly, when we added 0.556 sine squared alpha, add this to what we have here in equation 1, which is also 0.556 but cosine squared alpha, what we will get is that the sine squared alpha added to cosine squared alpha is actually equal to 1. Okay? And then multiply it by 0.556 is just equal to 0.556. It is that simple. Alright? And then, what happens to the other terms? Okay? Contained in equation 1, they are just retained. That is 2.22 minus 2.22 cosine alpha. So, we are able to eliminate the first angle beta and only have here the angle alpha. In short, we can determine alpha, okay? When we proceed in our simplification, we can find alpha, okay? So, what we did was just to add this 0.556 plus 2.22 and we get 2.78. Then minus 2.22 cosine alpha, alright? And then, we will isolate 2.22 cosine alpha, okay, by moving this to the left side of the equation and at the same time move 1 here to the right side. And what we will get is something like this. Alright? Moving 2.22 cosine alpha to to the left side, okay, will give us cosine alpha, and then divide the difference between 2.78 and 1, because 1 has been transferred to the right side, making it negative, and negative 1 plus 2.78 will actually give us 1.78. Okay, and dividing the whole thing by 2.22, we now arrive at this equation, which gives us okay, the working equation in determining the angle alpha using arc cosine. I'm sure you're familiar with that, okay? With your calculator, you can now determine the value of alpha, and that is equal to arc cosine of the quotient 1.70 divided by 2.22. Using your scientific calculator, you will get this value of alpha equal to 36.7 degrees. All right? Now, how do we determine angle beta? We can choose either equation 2 or equation 1, but we'd rather choose equation 2 because it looks much shorter and simpler, right? So, there we go. We just substitute the angle, all right? Sine squared beta is equal to 0.556 multiplied by the sine of the angle 36.7 degrees, and then square. You still square or get the square of the value sine 36.7 degrees before we multiply it to 0.556. All right. So this is what comes out. The value of 36 or sine 36.7 is equal to 0.598. Get the square of that, then multiply to 0.556. Okay, and then since we are looking for sine beta, we get the square root. All right, we get the square root of 0.199. All right, and what we get is 0.446. In short, sine beta is equal to 0.446, and then using arcsine formula to get the angle beta, we now have arcsine of 0.446 to get this value of the angle beta, 26.5 degrees. All right? Now, um, now that we know the two angles, we also got the value of the final velocity of um, the lighter or the smaller particle. So by plugging in those data into the equation for conservation of momentum, okay, uh, this is what we will get. Okay, conservation of momentum, which we earlier said that the conservation, what's this? The total momentum before they collided along the y is equal to 0. All right, this is along the y, and then that total momentum before collision must be equal to the total momentum after collision as far as the y component is concerned. Okay, so we simply uh, substitute the given or the quantities that we have here, okay, and then simplify, and finally what we get is that this part of the equation gives us, okay, um, the value for the momentum, okay, the value for the momentum amounting to 0.598 kilogram meter per second, and then for the y component downward or along the negative y axis, we also get 0.598 kilogram meter per second. In other words, when you subtract them, all right, what we get is 0. So that validates our conservation of momentum, the law of conservation of momentum as applied to the y component. Okay, 0 is equal to 0. So That means our answers, as far as the values of the final velocity of the lighter particle and the angle alpha as well as the angle beta, okay, we say that they are computed, okay, very accurately, because when substituted, no, to one of the equations, we are able to get, okay, or we are able to satisfy the law of conservation of momentum considering the y component. So that's it. We are done with our computation for uh, a problem involving kinetic energy as well as conservation of kinetic energy and conservation of linear momentum. Okay?